Alright, this LeetCode question is called partition equals subset sum. It says, given a non-empty array containing only positive integers, find if the array can be partitioned into two subsets such that the sum of elements in both subsets is equal. So for example 1, the output would be true because we can split it up into one subset that would have 1, 5, and 5, and that would equal 11, and the other subset would be just the number 11. So for example 2, the result would be false because we can't split it up in a way where the two subsets have an equal value. And we'll do this using dynamic programming.
Alright, let's do a quick example that's going to help us later. Let's say we have the numbers 1, 2, and 3. What are the total numbers we can come up with by adding up these numbers in different ways? Like I mentioned earlier, we can use dynamic programming to help us solve this. So what we can do is we can create a new array. And this array will represent the possible totals when we add up the numbers 1, 2, and 3 different ways. Alright, so before we begin, let's do this. Alright, so to reiterate, these numbers are answering the question, can we come up with these results when using the numbers 1, 2, and 3? And this is dynamic programming, so we need a base case. So the base case is 0. We basically just pretend that there are no numbers. So with no numbers, can you come up with the total 0? Yes, you can. And by the way, anytime we see a T, that means true, meaning we can come up with that total. And if we have F, that means false, meaning we cannot come up with that number. Alright, so let's begin. With only the number 1, can we come up with the total 1? Yes, we can. So we'll change this false to a true. Alright, and since we only had one number there, we can only have one result, so we'll move on. So now, with the numbers 1 and 2, which totals can we come up with? Well, if we only had the number 2, we can come up with a total of 2. But remember, we also have the number 1. So with 1 and 2, we can come up with the number 3. So we'll change the number 3 to true. Are there any other totals we can come up with the numbers 1 and 2? No, so we move on. So now we're at the number 3. With the number 3, how many totals can we come up with? Well, if we only had the number 3, we can come up with the number 3, but that's already true. How about with the numbers 3 and 2? Well, 3 plus 2 is 5, so we can come up with the number 5. So we'll change that to a true. How about with the numbers 3 and 1? Well, 3 and 1 will give us 4, so we'll change 4 to true. Is there anything else? Yep, the numbers 1, 2, and 3. 1, 2, and 3 would give us the number 6. So we'll change that also to a true. So with that, we can say that with the numbers 1, 2, and 3, we can come up with, again, a base case, which is 0, but also the totals 1, 2, 3, 4, 5, and 6. And if you look all the way to the right, there's no way we can come up with the total 7. And of course, that also means that anything greater than 7, we also cannot come up with, because we've already used every number in our original list. Alright, so let's get to the question at hand. It's asking if we can break down an array in such a way where the two subsets are equal. So for this example, if we broke it down like this, 2, 4, 1, 5, the two subsets are equal because they add up to the same thing. They add up to the number 6. Well, what is the number 6? If we just look at all of the numbers in the array, 1, 2, 4, and 5, and add them up together, they add up to 12. So in order to come up with equal subsets, the subsets would have to equal half of the total of the numbers in the array. So once again, the total is 12, so the question is whether we can come up with two subsets that both equal 6. So knowing that, what else can we say? We can say that if the array totals an odd number, then we cannot come up with two equal subsets. So we can add up all the numbers in the array. If the number is an odd number, we can immediately return false. Alright, so using what we learned in the last video, we can do this. We can create a new array which represents all of the possible combinations of the numbers in our original array. Except it's not a total of all the possible outcomes, and that's because it doesn't need to be. If we needed all of the possible outcomes, we'd need an array of 0 through 12 because 1 plus 2 plus 4 plus 5 is 12. But that's not what we need. All we actually have to try to find out is if any of the possible combinations add up to half of the total sum. So let's say we had the numbers 1, 2, and 3. If any of the combinations added up to 3, we would know that the other subset also equals 3. In this case, we only have to see if any of the combination sums add up to 6, because then we'd know that the other subset also equals 6. So really, we only care if this ever turns to true, meaning if any of the combination sums ever equal 6. All right, so let's begin. We start with the number 1. And just to make it easier visually, let's cross out the rest of the numbers. We're not actually doing anything in the code. We're just crossing them out to remind us that we haven't gotten to those numbers yet. All right, so what we're going to do is we're going to see if we can get to any of these combination sums with the numbers that we have. And we'll do that by starting at the rightmost index of the array and checking one by one all of the target combination sums and see if we can arrive at these combination sums using our numbers in the original array. And there's a very good reason that we're moving right to left instead of left to right, and I'll show you that soon. So our target combination sum is the number 6. So using the number 1, can we arrive at the number 6? The answer is obviously no. But how else could we have gotten to the number 6 using the number 1? If we only had the number 1, we couldn't. But what if we had previously come up with the number 5 in another combination sum? That would have given us the 6 we need. But we know we haven't come up with the number 5 yet because we only have the number 1. The number 5, though, we'll say is the complement. The complement, we'll say, is the number we would need to add on to our current number to get to our target number. So we'll actually write that as a rule up here. Do we have the complement somewhere? So like we said, the complement would be 5, but that's also false. So we cannot arrive at the number 6. All right, let's move down to the next number. Using the number 1, can we get the number 5? No, unless we've already come up with the combination sum for the complement, which again is the number 4, because 1 plus 4 would equal 5. But we have not seen the number 4, hence why we still have a false here. So no, we cannot come up with the number 5 yet. So let's move down to our next number, the number 4. So what we should do actually is to first check whether our target number, in this case the number 4, is already true. If it's already true, we can just move down to the next number. If it's not already true, then we can check to see if we have the complement. So no, it's not already true, and no, we don't have the complement. So we'll just move down to the next number. Same questions. Is it true already? No. Do we have the complement? No. So move down one. Next, can we arrive at the number 2? How would we know? Well, if it's already true, which it's not, or if the complement is true, which it's not. So we finally move down here. Now, can we arrive at the number 1? Is it already true? No. But can we arrive at it using the complement? Well, yes, because we know that we're on the number 1 and that we have its complement of 0. So 1 plus 0 gives us the 1 we need. So we'll say for the number 1, yes, we can come up with it using the number we have and its complement. All right, so we're at the number 1, and we just checked the target value of 1. Usually we'd move down to the next number, but there's no reason to, because we know that there's no way that we can arrive at the number 0 using only the number 1. So at this point, we should move on to the number 2, but before we do that, I'll show you exactly why we're moving from right to left instead of left to right. And to do that, let us reset all of the values real quick to how they originally were. Okay, so the values are reset, and now we're going to pretend that we're going to move from left to right instead of right to left. So we'll ask the same questions that we asked before. We're on the number 1. Can we arrive at the target value 1? First we check to see if it's already true. No, it's not. But now we check to see if we can get to it through its complement. So we have the number 1, and we have the complement 0. 1 plus 0 gives us the one we need. So now we can change this false to a true. And while we're doing this, pay attention to the number 1. So we've already visited the number 1. So now let's move on to the next number. Let's just take a step back. If we only have the number 1, could we arrive at the number 2? Of course not, right? But if we tried to apply the rules that we've set forth so far, what would happen? We would look at the number 2 and say, is it already true? It's not. But now we look at our complement rule. Our complement is right here. It's the number 1, and it is true. So we might be tempted to say that since the complement is true, that our number would be true. But we know that's obviously not right. What's happening here is that we're accidentally counting the number 1 twice, once as the target value and once as the complement. So let's go over that again, kind of in slow motion. We started here and we said, yes, we could arrive at the number 1. Then we went to the next one and we looked at 2's complement, which is the number 1, and saying, yes, since it has a complement, 2 is also true. But that's not the case. We counted the number 1 here, and then we accidentally counted it again here. Why does going from right to left avoid that? Again, pay attention to the number 1. We'll go by the rules that we've set forth already. So here, no, 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 no. Notice that we're not actually checking anything with the number 1 at this point. The number we're focusing on is the number 2. At this point, the number 2 isn't true already, and its complement is false. So now we'll move over to the number 1. Since the number 1 has a complement that's true, now we can make the number 1 true. So you see how that worked? Going from right to left, we only counted the number 1 once. But going from left to right, we would have counted it twice. All right, so let's reset this in order to move on to the number 2. Let's cross these out just to show that we haven't gotten to them yet. And we've just set up the complement correctly, since if we have 2 already, to get to the number 6, the complement would be 4. All right, so let's begin again. We're at the number 6. Is it true already? No. Can we get the number 6 using 2's complement, which is 4? No, we can't, so we move down. Is 5 true? No. Can we get to 5 by using 2's complement? No, so we move down. Same questions. Is 4 true? No. Can we get to it using 2's complement? No. Now we arrive at the number 3. Is 3 true? No. But can we get 3 using 2's complement? Well, if we look, we have the number 2, and we have its complement, which is 1. Remember, again, we got it when we were at the number 1 in this array the first time. So yes, 2 plus 1 is 3. So we can change this to true. So we keep moving. Now we're at the number 2. Is 2 true already? No. But can we get to it through its complement? Yes, because if we look at its complement is 0.
2 plus 0 is 2. So we'll change that to true. All right, so now we can just reset again. So our target is the number 6. So have we already arrived at the number 6? We haven't. But can we get to the number 6? Well, we're at the number 4, and we've already come across its complement, which is 2. 4 plus 2 is 6, so yes, we actually can get the number 6. And remember that the entire point of this question was to see whether or not we can get a combination sum of 6. We just got it, so we could end right now. But it's up to you to determine if it's worth it, if you want to put an if statement or something like that in your code that says if we ever arrive at the final number in the array, then we can just return true immediately. I won't, but that's just my personal preference. But because I won't, that means I still have to iterate through all of the other numbers in the array. All right, so let's continue. So the only thing left to do is to look at the last index in our array and see whether or not it's true. It is true, so our entire answer would be true. Meaning, yes, there is a subset of this array that equals the number 6. All right, let's get to the code. What LeetCode has given us is a function called canPartition, which accepts an argument nums. Nums is the array that we want to determine whether or not it could be split into 2 equal subsets. All right, so the first thing we have to do is determine the total that the numbers in the array add up to. So we'll say let sum equal 0. And then for every number in it, we'll just add every number to the sum. And now we'll check to see if that number is odd, because if it is, we cannot divide the array up into 2 equal subsets. So if it's odd, we'll return false. So if we get to this line, we know the sum is even, so we'll divide the sum by 2. You can imagine the sum now being the target sum we have to get to. So if the numbers in our array add up to 6, our target sum will be 3. So can we get a combination sum that adds up to 3? So now we need our combination sum array, whose length is going to equal sum plus 1. And why plus 1? Because we also need an index for the number 0. The number 0 being the base case. So we'll say let combos equal new array, and the length will be sum plus 1. And what we'll do is make every index false. So at this point, our combinations array will look like this, 4 slots, and we'll fill it, giving each index a value of false. But like we said before, the first index will have to be true. So that would look like this. And let me just add the indices to make it easier to read. So now we'll have to iterate over the combination sums array from right to left, seeing which combination sums we can come up with. So we'll say for let num of nums, and then for let I equal sum. We'll go while I is greater than or equal to num. And then I minus minus. So the outer for loop starts on the leftmost number in the nums array, and the inner for loop iterates from right to left and keeps track of the totals we can come up with when we add up the numbers in the nums array different ways. So at this point, this would be num, and this would be I. All right, so this line is the one that does the heavy lifting. It goes like this. Combos I equals combos I. So check to see if it's already true.
or combos I minus num. And combos I minus num is the complement we mentioned before. So to reiterate, it's saying look in our combination sum array and look at the index we're on. So right now we're at index 3. Is the index we're on already true? If it's already true, that's good. We can just move on to the next number. If it's not already true, look at the complement and see if that's true. So right now, if you look at the top array, we're on the number 3. We need to get to the number 3 in our combination sum array. To go from 3 to 3, we would add 0, which is the complement, which is right here. So have we gotten the complement in the combination sum? It actually is true. So at this point, we can change this to true. All right, so it's going to do that logic for every number in our combination sum array, and then it's going to move to the next number in our nums array and do the same logic again for the combination sums array. And it's going to do that over and over until it has checked every number in our nums array. So I'll do this part very quickly. All right, so all there's left to do now is to return whether the final number in the combination sum array is true. So return combos sum. All right, so let's run the code, see how we did. Looks good, let's submit. All right, so our code was faster than about 78% of other JavaScript submissions and takes up less space than 100% of them. As usual, the code and written explanation are linked down below. Also in the description are other good resources for learning algorithms. See you next time.